Hi everyone and welcome back. We have already looked at how to convert an NFA to a DFA intuitively, but in this video we are going to look at a formal way to do it. We are going to look at subset construction, which gives us a formal way to convert any NFA to a DFA. So let's start off with an NFA M, which is given by the 5 tuple that defines any NFA or DFA for that matter. So I have a set of states Q, I have a start state S, I have a set of final states F, I have sigma, which is my alphabet, and I have the transition function delta. And one very common practice is to use capital delta for NFAs, so I'm going to go with that. So this transition function is just it's represented by a capital delta to indicate that it's the transition function for a non-deterministic automaton and not a deterministic one. So now what I have is a set of definitions for my equivalent DFA. So a DFA equivalent to M, which is M prime, given by, so I have M prime, which is given by Q prime, S prime, F prime. Sigma, of course, will remain the same. My set of alphabets, my alphabet is not going to change. And I have a delta or a delta prime, let me call it. So this is my DFA that I'm going to construct. So this is my DFA. And I'm not going to dive into the proofs here, but after I give you these formal definitions, I'm going to try and convince you that these are true. So before we start, I want to remind you that an epsilon transition, the epsilon closure of a state is all states that we can reach with 0 or more epsilon transitions, and that a state always belongs to the epsilon closure of itself. So the first thing we have is our set of states Q prime for our DFA, that will be given by the power set of Q. So it is 2 to the power Q or power set of Q. These are just two different representations for the power set. So this I think we've already looked at, because every state in our DFA is going to be a combination, a set of states from our NFA. So that's the first thing. The next thing I have is my S prime, and my S prime is going to be the epsilon closure of S, my start state. And again, this is I think pretty intuitive, because if I have an NFA which has some epsilon transition to, let's say, Q2, and this is Q1, then of course my start state for the DFA will be Q1 comma Q2, assuming that I did not have any other epsilon transitions from either Q1 or Q2. So this will be the start state for my DFA. So let's get rid of this. I hope the start state being the epsilon closure is intuitive enough to you. And next I have my final state F prime. So now F prime is it will be Q prime, or I could say that it is K, let's say, which is a subset of Q. So I have K subset of Q, such that K intersection F, F is my final state for the NFA, the set of final states for my NFA. So K intersection F is not equal to an empty set. So once again, this just means that I'm taking all subsets of my states from the NFA, and I'm taking their intersection with the final states of the NFA, and I'm saying if the intersection is not phi, then that would be a final state for my DFA. Let's pause at this point and take a look at an example NFA, and then we can look at the transition function later. That's the only thing we are left with, because we've already said that sigma is going to remain the same, and we've defined all three of these. So we are just left with the transition function. Let's look at that later. First, let's take some NFA. So let's say I have an NFA with a start state Q0, which on 0 goes to Q1. On epsilon, it goes to a final state Q3, and Q1 on epsilon goes to Q2, which on 0 goes to Q3, and let's say this goes to Q3 on a 1. This is just a random NFA that I've drawn. So here, let's say my start state is Q0 for the NFA. So what I'm saying is my Q prime for my DFA will be the set of Q0, Q1, Q2, Q3, and then I will have Q0, Q1, that will be a single state in my DFA, and so on. And the last one that I'll have is Q0, Q1, Q2, Q3. That will also be a state in my DFA. So this is the number of states, these are the states in my DFA that I have. Of course, not all of these will be reachable, but in theory, this is how it is. And from here, you can see that if my NFA M has, let's say, n states, then my M prime is going to have 2 to the power n states. And there will also be a trap state here, or a phi state. So let's just call it the trap state. So I have T as well here. So that's how I have 2 to the power n states in my DFA. And now let's look at our final states. So we said that it is K, which is a subset of Q, such that K intersection F should not be equal to phi. So what do I do here? I take all subsets of Q, which are these right here. I've already made those for Q prime. So I take each one of them and I check whether their intersection with my final state is phi or not. And let me just write that my final state here is just Q3. So I need to check whether for the first one, let's say I have Q0. So is Q0 intersection Q3 not equal to phi? No, it is equal to phi, because they don't have any state in common. Is Q1 intersection Q3 phi? Yes, it is. So once again, this not equals phi is not satisfied, so I won't have that as my final state. What I will have as my final state, however, is Q3 itself. I will have Q0, Q3. I will have Q1, Q3, and so on. And my last state, this thing right here, will also be a final state. So that's just because it contains Q3, so its intersection with Q3 is not going to be phi. So this is about my final states, and now what we're left with is the transition function. So let's take a look at that. So the definition for the transition function is slightly complicated, but let me just give it to you first and then I'll explain why it holds. So I have a delta prime of k comma a, where k once again is a subset of q, or you could say that k belongs to q prime, which is the set of states for the DFA that I'm constructing, and a is a symbol from sigma. So here this is given by the set of epsilon of p, such that p is a state from q and delta of q comma a is equal to p for some q belonging to k. So I know this sounds slightly complicated, but let's just look at this with an example. And let's just look at the example of the DFA that we had in the previous page right here. Let me just size it down a bit. So I have this DFA right here. Sorry, I have this NFA right here. And what I'm going to do is I'm going to try and work out at least some part of delta prime using this definition right here. I also need an arbitrary union right here. We'll see why that is required. So for my first case, let me just take k as equal to q0, which is a subset of q, so that works. So k is equal to q0, and let me take a is equal to 0. So I want to know where does my DFA go from the state q0 on a 0 input. So what I do is I say that it is equal to E of p, where what is p? P is a state in q, such that delta of q comma a is equal to p for some q belonging to k. So what we start with is this q belonging to k right here. So I start with this. The only thing that belongs to k for me is q0. So I take q0 and I try to find out delta of q0 comma 0, because a for me is 0. So delta of q0 comma 0 is q1 right here. So this is equal to q1. So my p is now q1, and q1 does belong to q, so this part is not a problem. So what I need to do is I need to take the epsilon closure of q1, and I still have an arbitrary union of that. So what is the epsilon closure of q1 from my NFA? It is q1 and q2. So this is now equal to the arbitrary union of q1 comma q2, and my delta prime right here needs to give me a set of states which is any subset of q1. But here what I'm getting is, if you see right here, I have a set of sets of states. So if I had, let's say, epsilon of q1 comma epsilon of q2 and so on, I would have within these braces right here, I would have had multiple sets, which is why this arbitrary union is important. So when I take the arbitrary union of this part right here, what this is going to be equal to is just q1 comma q2. And intuitively from q0 in this NFA, where can I go on an input 0? I can go to q1 using this route right here, and from q1 I have a free transition to q2 without consuming any input, so of course I can go to q2 as well. So that's the first case that we've looked at, and let's just take a look at one more case to find delta prime, and then we can close off this video. So let's take the second case where k this time is, let's say my k is equal to q1 comma q2, which is the state that we got from q0 on input 0. So I have k equals q1 comma q2. Now what I do is, once again, let me just use a different color. So once again I start with q belongs to k. So this time I have two of those. So for my first scenario I have q is equal to q1, and now delta of q1 comma 0 is delta of q1 comma 0 is nothing, because in my NFA I don't have a transition at all, so that would be a phi. And of course I have the arbitrary union here. I have phi, and for the second case I have q is equal to q2 now, and now delta of q2 comma 0 is equal to q3. So I have epsilon of q3 right here. This is now just equal to the arbitrary union of phi and q3, because the epsilon closure of q3 is just q3 itself. It has no epsilon transitions at all. And this arbitrary union is now just going to be equal to q3, which is the only state that my delta prime takes me to with these values. So I can say that delta prime of the state q1 comma q2 comma 0 is equal to q3. And remember that this thing is a single state in my DFA, and this is also a single state in my DFA. So that's about subset construction. All of this gives us formal definitions for converting any given NFA to a DFA. But as far as we are concerned, it should be perfectly fine if you can intuitively convert an NFA to its equivalent DFA, and you don't need to remember all of these definitions. You can of course come up with an algorithm to do this conversion process for you. But I hope you understood how all of these mathematical definitions have been formulated. So in the next video, what we're going to look at is state minimization, which is another very important algorithm. And the reason it's important is because as we saw here, our final state was a lot of states right here, because it had Q3, it had Q0, Q3, Q1, Q3, it will have Q2, Q3, it will have Q0, Q1, Q3, and so on. That's a lot of states, and very often the only states that we need in our DFA are the ones that are reachable. So we don't need to make a DFA with all our unreachable states. So we look at state minimization in the next video. Stay tuned for it.